set of ordered pairs, domain is the x values, range is the y values. A function corresponds one x value with a y value. X's cannot repeat. That's what makes it a function, right? X's cannot repeat. So let's look at a few relations, and inside are the functions. Okay, so we're just going to say, is this a function? And we'll start with example A. We'll start with 1, negative 6 as an ordered pair, 3, 5, negative 2, 4, 7, negative 13. So they can list a relation as just a set of ordered pairs, just a list of ordered pairs there. Does this one meet the criteria to be a function? Or they need repeated x values? Or no repeated x values? So it's okay. It is a function. So this is yes, it is a function. And then they could also use a table to represent a relation. So we got a set of ordered pairs there. 4, negative 8, 3, negative 2, 6, negative 5, and then 4, negative 6. So a little more right here. 4, negative 6. Is that a function? No, because you got a repeated x value. It's got a different y value for that same x value. That's not allowed. So no. And the reason that we're using, I'm just writing it here so that we remember the repeated x value. All right, so set of ordered pairs, a table is another way that they can represent a relation. And then there's another way, it's called a mapping. And a mapping is just bubbles. You got an x bubble and a y bubble. And they put numbers in those, like 4, 6, 7, negative 3, 100, 200, negative 300. And then the mapping is they just draw arrows to create the ordered pairs. So 4 might go to 200, and then 6 to 100. 7 also goes to 200, and negative 3 to negative 300. So that's a mapping, and it's just another way to represent ordered pairs. You got 4, 200, 6, 100, 7, 200, negative 3, negative 300. Is that a function? Yes. Yeah, the x values don't repeat. You don't have two arrows coming from one x value, so it is a function out of that. So if there are two arrows coming from a mapping from an x value, then it's not a function. So no repeating x's. That's the key. Now, when they represent a relation or a set of ordered pairs using a graph, then we've got to do some other things. So let's look at a graph. I'm just going to sketch a graph. Yours doesn't have to be perfect. I'm not even using graph paper here because I'm just using a sketch. I'm not even going to label any points. So we got the x and y coordinate planes. That's all that is. And I want to draw a graph on there. So I'm going to use a pretty easy one to start off with. Just a nice straight line. Saw several of those on your lab today. So nice and easy there. That blue line there represents just an infinite set of ordered pairs. It's every ordered pair that blue line touches. That's what that represents. Okay? So it would be impossible for us to write out every single ordered pair that blue line says, right? So we couldn't check to see if repeated x values by writing it out and making a list. So we have the vertical line test. That's how you can see if a graph is a function. It's using the vertical line test. So what the vertical line test does is it checks for repeated x values. And what you do is you take a vertical line and you lay it anywhere on that graph. You try to find a place where if you lay that vertical line on there, it touches the graph in two places. If it touches it in two places or more, then it fails and it's not a function. So this one, if I take a vertical line and I just drop it right here, How many places does that touch the blue line? 1. Okay. Is there anywhere that I can drop a vertical line on that and it touch twice or more? No. So this one passes the vertical line test, and this is yes, it's a function. So using that vertical line test is how we can test a graph out of that. So let's look at one that might not pass. So just another coordinate plane sketch here. Doesn't have to be too precise. Okay, and then let's say it's this shape. Lips kind of squash circle out of that, but there's an equation for that. It doesn't matter what it is. But the question is that a function or not? No, we could easily find places that we could drop a vertical line on that and get it touching in 2 places. Right there, those 2 spots are where the x value is the same, but the y value is different. Okay? X values cannot repeat. Okay, so that right there, the vertical line test tells us that x values repeat there, so this is not a function because it fails the vertical line test. So vertical line test is going to be your way of checking graphs. Okay, checking graphs is with the vertical line test. All right. Now, when we get into functions, we start talking about domain of functions. Okay. And then we're going to talk about finding the domain when we have equations. All right. If we've got a list of ordered pairs, domain's pretty easy. You just write the x values out, you write the y values out. That's not hard to do. When we have equations, that becomes a little bit more difficult to write out the domain and the range of that, or the domain for sure. So what we need to know is that there are only 2 red flags that could ever come up to tell us what x values could mess up a problem. Okay? What's the only number that we could not ever divide by? Say that again. 0. We can never divide by 0. So the red flag that comes up there is you have an x in the denominator of a fraction. So the bottom of a fraction. You've got an x in the bottom of a fraction. That red flag comes up, then you've got to do something about the domain. Okay? There's another red flag that comes up. An x on the inside of a square root. Okay? If an x is on the inside of the square root, if x were negative, what does the square root of a negative number get us into? Square roots of negatives. That gets us into the complex number system. With the i's, I remember taking like the square root of -4, and it's 2i, that sort of thing. Well, when we're talking about domain, we're talking about x values on the coordinate plane. So we're not concerned about the complex number system. We're only concerned with the real number system. So these 2 things, if they come up in the equation, then we've got to do something about it in order to get the correct domain. All right. So when we're doing this, if there's no red flag, then the domain is quote unquote all real numbers. And that's going to be from -infinity to positive infinity. That's how we write that, using this thing called interval notation. So, no red flag, it's all real numbers. Everybody starts there. Before you start working a problem, you're saying, okay, the domain, before I look at it, we're going to assume it's negative infinity to positive infinity. It's all real numbers. Okay, we'll assume that at the beginning, and then we look for the red flags. If there's not a red flag, then the domain stays that. If there is a red flag, there are certain things that we need to do. Okay, so we're going to go through what do you do if there is a red flag on that. So let's start with this example. Example F. Let's say we had f of x is equal to x plus 4. Just a simple linear equation there. It's kind of similar to some of them we saw in labs tonight. So here we have this problem. We look for an x in the denominator. So that implies that there has to be a fraction in the problem for that to happen. No fractions in this problem, so that's out. That's not going to happen. An x inside of a square root. There's no square root in this problem. So I don't have any red flags for that. So that since there's no red flags, then my domain is going to be all real numbers. And we're going to write, I'm going to show you how I want domain written. One way is with what's called set builder notation. Set builder is what this is called. And the way it works is you make a little curly brace, and then you do x, and then a straight up and down bar. Straight up and down. Looks kind of like an absolute value, but it's only one side of it. Just straight up and down bar. And then we're saying that it's all real numbers. X is an element of the real number system. That's how you do it. Remember this epsilon that we used last week? That little C with the line in the middle. That means X is a real number, and that R has two little bars on it. So just make yourself an R and then put another bar behind it. That says all real numbers is what that means. Okay, so that's abbreviation for all real numbers. Okay, and then you put curly braces on the other end. That's set builder notation. We're also going to work in what's called interval notation. I-N-T-E-R-V-A-L. Interval notation. Interval notation is number line based. When we talk about interval notation, we're thinking about a number line. So on a number line, if you were going to mark all real numbers on a number line, you would put an arrow above everything, right? And the interval notation for that says, okay, this keeps going forever that way, which would be negative infinity. This arrow keeps going forever that way. That would be positive infinity. Okay? So negative infinity to positive infinity is the interval notation. And we use a parenthesis on that because we can never get to infinity. Every time you think you're there, you say one, you're not there. Okay? So negative infinity to positive infinity with parentheses in there. If we have a number that we're actually stopping at and using, then we'll use a bracket to do that with the interval notation. We'll learn this as we go, but be able to bounce back and forth between both of them. This particular textbook does bounce back and forth between them as well. So we're going to be able to bounce back and forth between set builder notation and interval notation. We're going to write every answer in both of them just to get the practice to do them. Okay. My high school kids have been working with them on transitioning over to interval notation a little earlier in their math careers, and they seem to be liking interval notation better because a lot of times it's shorter, but sometimes it's not. So it just depends on the problem. All right, so let's look at example G. We're going to find the domain of this function. F of x is equal to 5 over x plus 2. Well, remember we got red flags that could happen. The red flags are an x in the bottom of a fraction or an x inside of a square root. Well, here we got a big fraction, and lo and behold, look what's in the bottom. It's got an x in there. Okay, so there's a problem. So we've got to figure out how to describe the domain to avoid that problem x value. The problem with division is you cannot divide by what number? Y'all told me earlier. 0. So what we've got to find out is what number would make the denominator 0. So you take the denominator and set it equal to 0. We're trying to find when does x plus 2 equal 0. That's what we're trying to find. Okay? So take the bottom part, set it equal to 0, and solve that equation. So we're going to subtract 2 and x. When x is negative 2, then we'll have a 0 in the bottom. And that's the problem number. Okay? Negative 2 is the problem number. So the domain in set builder notation, you'd have x such that x cannot equal negative 2. That's how you write that in interval notation. When we solved that, we said, okay, when x is negative 2, that's when the bottom part is going to be 0. So that's the number we can't have. Okay, we're going to use every number except for negative 2. That's how you write that in set builder notation. In interval notation, let's look at the number line, because I think this helps you understand the interval notation. If the answer cannot be negative 2, on a number line, what goes above the negative 2? An open circle, right? But it can be any other number. So that could be any of these numbers this way or any of these numbers that way, right? Now, in interval notation, what that's saying is, okay, what's all the way out here? What number? Or idea? Way out there. Negative infinity is way out there. So we're starting at negative infinity. We put a parenthesis on that one because we can't get there. We'll always be just a little bit short of infinity. And then we're coming across the number line. We're going all the way until we get to the negative 2. And we've got to skip negative 2. The way that you skip a number in interval notation is you're going to put a comma. And then the number you're going to skip. I'm skipping negative 2. I'm skipping that number, meaning I'm not using it, so I'm going to have a parenthesis on that. Okay. Then I've got to pick up from there and use all of these numbers from negative 2 this way. So it'll be like negative 1.999999. That's one of our answers. So we've got to take that into account. So we're going to use a U for union, like we did with the set stuff. And then a parenthesis, negative 2. And then what is way out here? Positive infinity. So this is one of those cases where the set builder is a little bit shorter than the interval, but the idea is the same. They both mean the same thing. X cannot equal 2. This says all the numbers until you get to negative 2. This part skips negative 2 and then goes on to positive infinity. That's what we're trying to communicate that. So the domain is that. Okay. So let's say x in the denominator. We're going to set the denominator equal to 0. Solve. That's how you're going to find what number is cut out of the domain. Okay. Let's look at the next one. F of x is equal to the square root of x minus 5. Well, there are only 2 red flags that can happen. One was x in the denominator. We just saw that. The other one was an x inside of a square root. That's what's happening here. So when we have an x on the inside of a square root, we remember that we can only take square roots of numbers that are not negative. What numbers are not negative? Obviously, positive numbers are not negative, right? That's a given. What other number is not negative?
0.
Mm-hmm. 0 is not negative. So what we've got to do is find out when is that not negative. So we take the stuff that's on the inside here, and we're going to take it, x minus 5, and set it greater than or equal to 0 using an inequality symbol. If we solve this, this will tell us the x values that work. Okay, it'll tell us, hey, these are the ones that you can use. Okay, so how do we solve that? Add 5 to 0. X is greater than or equal to 5. Those are the numbers that will work inside of that square root symbol. Okay, so X has got to be greater than or equal to 5. And this one, when we start saying the domain, in the set builder notation, this one's easy again. All you got to do is say, take that inequality and just put it in there. All x's such that x is greater than or equal to positive 5. That's what that says. You take your inequality straight into there. Interval notation. What's the smallest x value that we could use according to that inequality? 5. 5 is the smallest one we can use. So that means our interval notation is going to start at 5 and go up. And if it goes up, where's it going to? Positive infinity, right? The only difference here is we have an equal to mark. Because if we had positive 5 in there, 5 minus 5 is 0. We take square root of 0, it's 0. Right? So that works. So instead of a parenthesis right here, we're going to put a square bracket right there. That means use the 5. It's one of the answers. So if you got an equal to mark, you're going to have a square bracket. Okay? No equal to mark or a not equal to, you're going to have parentheses. Okay? We're finding the domain of a function with a square root in it. Okay? Take whatever's under the square root, set it greater than or equal to 0. Solve it. That's going to give you your domain. All right, let's do one more of those. And maybe 2 more. I don't know. F of x is equal to 6 over 2x plus 7. And we're going to find the domain of that. Heck, let's put plus 5 out here on that outside. See if it makes it look harder. It makes it look tougher, but it doesn't change anything. What part is the only part that's going to mess something up? The 2x plus 7 in the bottom. That's the only part that's going to mess something up. So we need to take that and do what with it?
2x is 0.
Not 2x is 0, but to find out when is 2x plus 7 equal to 0. When is that going to happen? We set that equation up and solve it. First step. Minus 7. 2x equals negative 7. Divide by 2. Get a fraction, negative 7 over 2. Leave it as a fraction. Don't convert to a decimal. Leave it as a fraction. So in our domain, set builder notation, what goes on the other side of the bar? Goes over here in this area. Good job. All right, so the set builder notation, that's whatever we get when we solve that, that's what x can't be. And we got the denominator problem. Okay? Let's get that in interval notation. What number are we skipping? -7/2. So we're using every number except for that one. So anytime we're skipping a number, this is what happens. You got that U and then parentheses with that number in both spots. That's how you skip a number in the domain. Always going to be a U, never going to be an intersection. So it's always a U. What's that? All right. So there's our domain for that one. Let's look at the next thing, evaluating functions. Same section, just a different topic inside that section. Evaluating functions. This is function notation. When you're dealing with function notation, f of x is the same thing as y. Okay, so when we talk about x and y, f of x is the same thing as y. All right. When we've got an example, let's say, what letter are we on? J. F of x is equal to 3x minus 7, something pretty easy. And they want us to find f of -2. What that means is find the y value when x is -2. That's what they mean. So it's another way of writing an ordered pair is really what we're dealing with here. Function notation is another way of writing an ordered pair. It gives you the x value in the parentheses, and you find the y value that goes with it. Okay? So f of -2 means take -2 and put it in the place of x. And just work that out, just that side. This is not f times 2, it's f of -2, meaning x is -2. Find me the y value that goes with it. So that would be -6 minus 7 should be -13. So f of -2 is -13. That's what we're looking for. I want you to understand that it creates an ordered pair. The ordered pair would be -2, -13. X and Y. All right. Function notation, just a different way of writing an ordered pair. It deals with when you got equations that are functions, how you can write some ordered pairs. It's a very descriptive way of finding the y value for a certain x value. That notation there. Let's do g of x is equal to x squared minus 3x plus 7. And we want to find g of -4. What do we do with the -4? Yeah, put it in everywhere there's an x, put a -4. So this is just like evaluating expressions. It's just in the context of a function notation. So -4 squared is what? +16. -3 times -4 would be +12, and then plus 7. 28 plus 7. 35, is that right? That's what we're looking for, is a function value. When we've got an equation, function value is really easy. You just plug it in and work it out. Some folks get a little sideways, as I like to say, when they don't have an equation, but they've got a relation written there as a set of ordered pairs. But I want to show you it's just as easy It just looks different. It's weird because you're not having to do any work. You're just having to look for something. Here's our function, f of x, and it's a set of ordered pairs. -3, 5, 0, 3, 3, 1, and 6, -1. Okay? If they wanted us to find f of 3, what does that mean? So find the function where x is 3, right? Where is x3 at? That one right there, right? 3, 1. So the answer to f of 3 is 1. So it's taking that idea of it. It's an ordered pair. It's really an ordered pair there. If they ask me to find f of 6, what's the answer to that? -1. So you just follow it to the ordered pair out of that. For whatever reason, every year it seems I get a lot of folks get sideways when it's that, and it's just following the ordered pair. They give you the x, you find the y. That's all it is. It may be a little bit more complicated, and that may have a longer list. It may be harder to find, but it's the same idea. It's not too bad there. All right. The next thing in this section, last thing in this section, is talking about intervals of increasing, decreasing, and constant intervals over a graph. So I'm going to sketch a graph. I want you to just make yours look close to this. It doesn't have to be perfect. I'm not using graph paper. I'm just going to draw a coordinate plane and draw a little bit of a picture here. So what letter are we on here? M. Example M. I'm going to draw a coordinate plane, sketch one. Heart rate go down too low. I'm dying. All right. Okay, now on this coordinate plane, we're going to draw a little bit of a picture. So I'm going to draw a little line that goes down and to the left like that. I'll put a dot right there. That ordered pair is -2, 6. I'm just telling you that's what it is. Then I'm going to draw a flat line across and put a dot right there. And that ordered pair is 7, 6. And then I'm going to draw another line that goes down and to the right, just like that. Okay. What we're going to do is we're going to talk about intervals or intervals that increase, decrease, opposite of that, and are constant. And this picture has all of those in it. Okay. So when we look at a graph, we can look at pieces and decide whether it's increasing or decreasing, okay, or if it's constant. And when we do that, we read the graph like you read a book from left to right, or like most people read a book from left to right, okay? So left to right is how we're going to read that. So when we look at this graph, and we start over here on the left and we're reading across, what is this first interval doing as we read it left to right? Is it going up and to the right or down and to the right? As we move to the right, we're moving up, right? So that's an increasing interval. What is that interval? Since we have an arrow pointing this way, what x values would that eventually get to? -infinity. Where does it stop increasing at? At that ordered pair up there at -2 is the x value. When we're doing intervals of increase, decrease, or constants, we're looking at X values. The Y values tell you up and down, but the X values are where you're at on the graph. Okay. So when our intervals are going to be X value intervals. Okay. Now, the next interval looks like right here. What's it happening from -2, 6 all the way to 7, 6? It's constant. It's staying flat. Constant is flat. So that interval would be from -2 to +7. We use parentheses on those because who knows whether it's which one is the stopping place for increase and the starting place for constant. Can't tell. It's just the point where it changed direction. So we're always going to use parentheses on the intervals of increase, decrease, and constant. Okay. And then at 7, the graph starts going down and to the right. So that's an interval of decrease. So 7 to where? Positive infinity. You can, on some more complex graphs, have intervals, more than one interval of increase, more than one interval of decrease, more than one constant interval. There's not a rule that says you'll have one of each. You may not have any on some of those. Okay, so intervals, X values are your intervals. So intervals, remember X values. Domain, X values, intervals of increase, decrease, or constant. You're going to use X values as well. All right? One section down, 2 to go. All right. I'm going to use some graph paper on this one, just so I can draw my graphs a little bit more precise with this. This whole section is basically an introduction to different kinds of graphs. And it's a very short section. Okay, so it's just basic information about various different functions that we deal with. All right, so I'm going to use some graph paper. You're welcome to use that, or you can use regular. I don't care. It doesn't matter to me. It's your notes, not mine. I'll try to make this as painless as possible. All right, so section 2.6 is where we're going next. Basic functions and their graphs. And I'll try to incorporate some stuff with the graphic calculator as we go with this too, okay? So when we start talking about functions and graphs and things, there's this thing that comes up. It's called continuity. Think about continuous. That's the root word there, continue. So C-O-N-T-I-N-U-I-T-Y, continuity. Continuity is dealing with a function over an interval. That interval may or may not be the whole domain. They may tell you to only look between the X value of 7 and 106. Or they may tell you where to look, but they may ask you about the entire domain for it. So it could be various things there. So continuity is, we'll define it this way, continuous functions over an interval. Sometimes that's domain. Can be drawn without leaving the paper. Don't pick up your pencil. That's if something is continuous, you could trace the graph without picking up your pencil. You never have to pick it up and move to another spot. You can follow it. It flows all the way through. Continuous means it doesn't stop. It continues. It doesn't have an empty spot in the graph or anything like that if it's continuous. Some pictures, just some basic sketches of some graphs. just going to draw a coordinate plane here and draw a few examples here. I'm just plopping those on there. Not really, they don't have to be locked into the grid there. So here's an example of a continuous graph. I didn't pick up my pencil at all as I drew that. You could trace that along without picking up your pencil. That is a continuous graph. Here is an example of a discontinuous graph. That one is discontinuous because if I try to trace it, I've got to stop, pick up my pencil, and move to another spot and start again. So that's discontinuous. Okay. So here is continuous. This is called discontinuous. And then here is a sneaky one that's discontinuous. I'll put a little circle in the middle of it there. That one's sneaky because it's just a little empty circle there. You've got to jump over that number that's there. So this is a discontinuous. There's a break in the line, break in the curve that's going on there. So continuous, no breaks in the curve, no jumps, no holes, nothing, just flows. Discontinuous, it does not. It's got some skips, okay? All right, so we're going to look at some basic functions and their name, and then we'll draw a picture of them and talk about their domain and ranges. Okay, so that's what this section is about. It should take us just an incredible amount of time here. So number one, I'll use regular numbers instead of Roman numerals. No sense in overthinking things. Number one is what's called the identity function. The identity function. Its equation is f of x, that's the same thing as y, is equal to x. Okay. Y is equal to x. The graph of that, I'm just going to draw a small coordinate plane over here. I'll plop one of those that I copied and pasted a while ago on there. All right. The graph of that goes straight through the origin. Try to draw this really good. Whatever x is, the y is the same number. That's why they call it identity. Whatever the x value is, y is the same number. Okay? So when x is 3, right here, y is 3 as well. So that's why it's called the identity function. Okay? The identity function has a domain from negative infinity to positive infinity. That's all real numbers. The range is the same. Okay. So one of the things that you'll have to do is recognize and know the name of different functions by their graph and then know about the domain and the range for them. Okay. So the identity function. Number 2 is the squaring function. The squaring function squares x. It's f of x is equal to x squared. Okay. The graph of that starts at the origin. And it's this U-shaped. It's called a parabola. You may have seen that graph before. I hope you have. The squaring function. Now, looking at that graph, what's the domain of it? this way, but the domain, remember, is left to right. So how far is this going out to the left? It's going forever that way. It's slowly getting there. It'd be slower and slower because it's getting steeper and steeper on the side. But it's going to the left forever. Over on this side, it's going up and to the right, but it's going to the right forever, right? So our domain would be from negative infinity to positive infinity. Our range for this one range is y values. So we read from bottom to top. So when we look at range, domain, you're going to read from left to right. Range, you're going to read from bottom to top. And what's the lowest y value? 0, it's right down here. And then the y values go which direction? Up toward what? Positive infinity. So the way we would write that is 0 to positive infinity. We would put a square bracket on the 0 because it's included. It's a point right there. The squaring function looks like that. It's got that shape to it. It's a U out of that. Pretty boring names here. The third one is called the cubing function. The cubing function, instead of x squared, it's going to be x cubed, which is the third power. Okay? The cubing function, nice looking graph. Gotta get it lined up good there. That's what the graph looks like. A little swerve there. Domain, negative infinity to positive infinity. Slowly get there, but it will eventually get there. The range, a little quicker, negative infinity to positive infinity. The cubing function, x cubed. Got that shape to it. The idea is tie the name to the equation and to the shape. Tie the name to the equation and the shape. That's what you need to be focusing on when you're studying. The fourth one, pretty basic sound in here, square root. The square root function, f of x, is equal to the square root of x. Its graph looks like that. It's kind of like half of the parabola turned on its side, half of the squaring function turned on its side is what that looks like. Okay? Domain starts at 0, goes to positive infinity. Range starts at 0, goes to positive infinity. This one's a little different on domain and range than some of the others. Okay, we did square root. The next one will be cubed root. Bless you. Cubed root. Not roof, root. Handwriting there. F of x equal to the cubed root. They put this little 3 on the outside there of x. Graph of that stuff. Take the cubed or the cubing function and lay it on its side. That's how this one works. The graph looks something like that. Lays the cubing function on this side. Okay. The domain, negative infinity to positive infinity. The range, same. Well, last one here. Absolute value. F of x. Absolute value symbols of x. The graph of that is a V shape. Right here in the center, a V shape. There's the absolute value graph. The domain for that, negative infinity to positive infinity. The range, what do we know absolute value always does? Turns a number what? Oh, it's a distance away from zero. So the range, the y values that we get back from any x value that we pick, start at 0 and go to positive infinity because it's going up. If we read that graph bottom to top, that's how that works. Okay. You need to be able to recognize the graph along with the equation and the name of it. Okay, that's what you need to be focused on that section. It's more of an informational kind of thing there. There's some problems that I'll write up in a little bit about the from the book on that. So, but we're going to take those basic functions, and in this next section, last one of the night, 2.7, we're going to talk about transformations and translations. In a past life, mathematicians used to call this graphing techniques. But because we live in a technological society, we have graphing calculators that can graph pretty much anything we can type in. Okay, so graphing techniques is not necessarily where we're at with this. We're looking for general understandings of glancing at an equation and knowing what it did to what's called the parent function, which is one of those basic functions that we just talked about. So a parent function, if I say that, I'm talking about one of the basic ones that we just talked about. Okay, parent function, basic. Okay, so when we talk about the transformations and translations that we're dealing with, we're going to talk about stretching the graph vertically, horizontally. We're going to talk about taking a graph and shifting it vertically and then left and right. We'll talk about reflecting it across the x and y axis and different things and what the equation looks like when that happens. Okay, so we'll start with stretching and shrinking vertically. Okay, so a vertical, one thing that will help you in learning this stuff, understand that things that are vertical happen on the outside. Things that are horizontal happen on the inside. Okay, you'll keep that in mind as we go through this. It'll start making some sense. Vertical, outside. So that's a shift up or down. That's a stretch like this or a compression like this. Okay? Those things happen on the outside, the way the equation works, the changes. Horizontal things happen on the inside. So that's taking a graph and shifting to the right or to the left. And it's also taking it and compressing it vertically or stretching it or compressing it horizontally or stretching it horizontally, okay, or flipping it across the y-axis is a horizontal movement. So vertical things happen on the outside. Horizontal things happen on the inside. If you'll keep that in mind as we go through this, I think you'll start to see a pattern that's developing, okay? So let's start with vertical stretch. A vertical stretch. You multiply the basic function or the parent function by some number, and that number has got to be greater than 1. If you're going to stretch something vertically, you're going to make it taller, right? What does f of x represent? A y value. If you're going to make something taller, you're going to take the y values and make them bigger, right? So multiplying by something bigger than 1 will make your y values bigger, so it will stretch the graph out. You guys, I'm going to be dating myself here, but you ever play the Silly Buddy? They still do. I do. That's fun for me too. But remember, we used to do this when I was a kid. I always got the paper on Sunday, and I always got excited because we got to play Silly Buddy after church on Sunday. And you take the funny papers out, and you take that Silly Buddy and roll it out, pat it out like a little pad of it, and you press it down on the paper, and then you pull it up, and the picture came back on the Silly Buddy, right? So when you did a vertical stretch, it's like taking that Silly Putty, you got that picture of Garfield or maybe Charlie Brown or something on there, and you stretch it vertically, it made the picture do what? If you stretch Charlie Brown, what happened to it? He got skinnier, didn't he? Or Garfield did, for sure, right? So when you stretch it vertically, it makes it look skinnier on the graph out of that. So a vertical stretch makes your graph look skinnier. Let's take one of our basic functions, and I'm going to kind of try to incorporate the calculator here as we're doing this. So with the graphing calculator, you can graph things and look at what's happening real quickly and easily. So I want to help you understand some of this by showing you those graphs. So if you got your graphing calculator, get that out. Hit the y equals button, which is the one right underneath the screen on the left, top left, right underneath the screen. So the screen would be normally right here. I've got some stuff already in there. I'm going to clear that out. If you did that and one of these plot 1, plot 2s, and plot 3, if they're darkened in, raise your hand. It's okay. We just need to turn them off. Okay? All right. So what you want to do, if you've got one that's darkened in up there, that plot 1, plot 2, plot 3, press the up arrow until you find the one that's like darkened in. So like if my plot 2 was darkened in and I hit y equals and I showed up here, I need to turn plot 2 off because it's going to mess up my graph. So I'm going to press the up arrow and go over to that one and where it's blinking and then hit enter and it will turn it off. Okay. If you've got plots on, it can mess up your graphing out of that. So you want to make sure those are off. Okay. So I'm going to clear this out from what I'd done sometime. I don't know if that was today or some other time. All right, so let's take the basic, the squaring function. What was the equation of the squaring function?
X equals x2.
X to the second power, x squared, right? So in y1, I'm going to type x squared. So with the graphing calculator, to type x squared, right there beside that green alpha button, press that to get an x. That's how you get an x. And then I need that squared. So I've got a squaring button right there above where it says log. We'll hit that button to get x squared. Okay. Then I'm going to hit graph. And I see that same picture that I sketched earlier for us, right? It's that same kind of shape. Okay. Now what we're going to do is we're going to do a vertical stretch on that. So we're going to multiply that by a number bigger than 1. Okay. So I'm going to leave the blue in there. I'm going to hit y equals one more time. Then I'm going to go down here to y2, and I'm going to put in a different function, one that's got a multiplier on it. So I'm going to multiply by 3 is a good number. I put a 3 times x squared. So I'm going to hit 3x squared. Didn't put a times button or anything like that. I just said I typed a 3, then hit an x, and then hit a square. That's how I got there. Okay? What I want you to see is the difference in the two. When I hit graph, the original one is already there. That's the blue one that I drew earlier. And then here's this one. Look at it. The silly putty and stretched it this way, made it skinnier. That's what it looks like to do a vertical stretch. That it pulls that graph and makes it skinnier. That's what a vertical stretch looks like. Okay? So vertical stretch, you're going to multiply by something out in front, outside. It's got to be a number bigger than 1. So example of that might be just like what we did there. F of x is equal to 3x squared. That's an example of a vertical stretch. That's what the equation would look like. So the idea is that you would be able to glance at that equation and without graphing it, know that, hey, that's taking the squaring function and doing this to it. But you learn that fact that it's doing that, because that will speed you up in some other things later on, okay? Another example might be taking the absolute value function, absolute value of x, and just multiplying by something. You could multiply by 6. It's going to take that V shape, and instead of being the normal width, it's going to stretch it vertically. So is it going to go skinnier or wider? Vertical stretch is going to make it look skinnier. Okay, so anytime you multiply by a number bigger than 1 out in front, it's going to make the parent function skinnier. It's a vertical stretch. Vertical stretch. Okay. Let's stay in the vertical world here, and let's talk about a vertical compression. If you compress something, you're squishing it down, right? So when the silly putty was a little difficult to do this with. So when you pulled that off and you had a picture of Garfield, if you compress, it was hard to compress and get the picture to show up because it would just hold up. But the idea was that if you pressed it down, what would happen to the picture? Stretching it up would make it skinnier, so pressing it down would do what?
Make it fatter.
Make it fatter, make it widen out, right? So that's what a vertical compression is going to do. And the way that it looks is you take some number and multiply it on the outside, but that number has got to be between 0 and 1. I don't know why I wrote an X there, not an A. That number's got to be a small fraction. Things that are between 0 and 1. What numbers are between 0 and 1? Give me an example. 0.5, 2/3, 1/8, 9/10, 0.9. Any of that stuff. That's a number that is going to be a vertical compression if you multiply by it on the outside. Notice I'm saying outside because that number's out in front. Okay. Examples related to the ones that we just talked about. If we took the squaring function and we said 1/3 x squared. If we look at that on the graph, and instead of putting a 3 there, I type 1 divided by 3 x squared. I'm going to retype that. 1 divided by 3 and then x squared. That's 1/3 x squared. That's what that says. Hit a graph. The blue one is the original. This one is the one that's been compressed. Pressed it down, it spread out. That's what a vertical compression does. Multiplying by a small number on the outside. Okay. Same thing as if you did a small number on the outside, like 1/2, or if you, let's do a decimal, 0.5 absolute value of x. That's a vertical compression because that number is smaller than 1 but bigger than 0. Between 0 and 1. So vertical compression, vertical stretch. You might hear me screw up and call it a shrink. That's what we used to call it when I first learned it. That they didn't say compression. May have been just because I was from Adamsville, Tennessee, and we don't complicate things mathematically down there very much. But compression is the proper term, and that's what I'll try to use every time. Okay. Now let's talk about horizontal movement, the same kind. Okay. Let's do a horizontal stretch. A horizontal stretch, things happen on the inside. So it's going to be f of a times x. That a is on the inside of the function. Okay, it's on the inside of the function. That a to be a horizontal stretch get wider, right? So it's going to look a lot like a vertical compression. So one of the reasons that we still talk about this, even though we've got the graphic calculator to do all those graphs, is because when you look at a graph, a horizontal stretch and a vertical compression look the same, right? So I'm widening out the graph no matter which way what I'm doing, but the equations look different. So knowing which one is happening is important, okay? So we're going to take that number, and to be a horizontal stretch, then that number has got to be between 0 and 1. It's got to be a small number. So an example of that would be like taking the squaring function and putting a 1/2 on the inside and then squaring that. We look at that on the graph. Got the parent function there at the top. I'm going to put parentheses 1/2 x, close parentheses, squared. Original, there's the horizontal compression. That looks just like, or a horizontal stretch, looks just like a vertical compression on the graph, but you can't tell until you go look at the equation, and then you can tell which one it was. Okay, so horizontal stretch and vertical compressions look the same on the graph, but the equation, the number you're multiplying by, is on the inside for horizontal, outside for vertical. Okay, a horizontal compression same idea. You're multiplying by a number on the inside, but that number is bigger than 1. Okay, a horizontal compression. Excuse me. No allergies. Good times. All right. So example of that would be like taking f of x and maybe absolute value of 3x, like that. If we did that, I'm going to show you how to do that with the calculator. So I'm going to clear out the parent function. To get the absolute value marks with the calculator, oops. In y equals, you're going to hit math. You're going to press the right arrow key, and that first option, ABS, stands for absolute value. Okay, I'm going to do that again. I'm at y equals. I hit the math button, which is right underneath the green alpha button. And then I'm going to take the absolute value of a number, first option, and it puts the absolute value marks in there. If you've got the most up-to-date operating system, which I think is 2.55 on the graphical calculator, it'll do that. If you don't, maybe next week, or we can update those. The TI board you can update, so we'll not be able to do that next week. All right, so I'm going to put an X in there. That's the parent function. We see that V shape. I'm going to go to Y2, and I'm going to put the absolute value, so math, number, ABS, and I'm going to put 3x. Compression. Pulls it in, makes it skinnier. That's what that does. Number multiplied on the inside, that's a big number. It's going to be a horizontal compression. Notice that's the opposite. When you multiply by a big number on the inside, that's the opposite when you multiply by a big number on the outside. Horizontals and verticals do opposite things. Okay. All right. So there's shrinks, compressions, or stretches out of that. So horizontal and vertical. Let's talk about reflections. I'm doing the harder parts first, and we'll get to the easier parts after this. Okay. All right. Reflections across the x-axis. Put a negative on the outside. Across the y-axis, put a negative on the inside. So across the x-axis, where the x-axis is horizontal, like this, if I'm going to reflect across that, if I start up here and I reflect across the x-axis, that's going to end up down here. That changes the sign of the y values. Okay, so that's a vertical movement. Notice how it's on the outside. The negative's on the outside for across the x-axis. That's a vertical movement, so it's on the outside. Across the y-axis, the y-axis is straight up and down. If I start on this side and I reflect across over here, the y values didn't change, but the x values changed signs. So that's on the inside. That's a horizontal movement. Y-axis is a horizontal movement. X-axis is a vertical movement. So outside for the x-axis, inside for the y-axis. Very, just there's not much to that other than that. Okay. Now, let's get to the next thing. Next type of translation or transformation that can happen is shifts. So a vertical shift. A vertical shift takes the original function and adds something to it, the outside. Okay? Vertically, B units. Okay? Example. F of x is equal to x squared plus 3. That plus 3 is going to go, it's going to shift it up 3 units. That minus 5 is going to shift the absolute value graph down 5 units. A vertical shift is going to be on the outside. Vertical shifts are on the outside. If you add, it's up. If you subtract, it's down. That's the way it always goes. Vertical shifts. Adding on the outside is up. Subtracting on the outside is down. A horizontal shift. Take the function and you add something on the inside. So we'll say plus b. That moves it to the left. You take the original function and you subtract on the inside. That moves it to the right. Okay. Examples. Absolute value of x plus 3. That would be to the left 3 units. X minus 5 squared. That's taking the squaring function and subtracting 5 on the inside. So that's going to move that squaring function to the right 5 units. Shifting it left, right, up, or down, depending on where you're adding and subtracting at. Okay? So, let's do some work with that, okay? We want to describe the transformation. We'll call this example A. I don't know where we're at. F of x is 3x squared minus 7. Okay? So this is a transformation on the squaring function. We're going to tell what all happened to this thing. Okay? So what does the minus 7 on the outside do? Outside would be down, so that's going to be down 7 units. What does the 3 on the outside there do? Vertical stretch. Okay. Vertical stretch because we're multiplying by 3 on the outside. That's a number bigger than 1. Okay. A number bigger than 1 multiplied on the outside is going to be a vertical stretch. The minus 7 on the outside is a vertical shift down 7 units. Take this one. 1/2 parentheses x plus 4 to the third power plus 13. Okay? This one has a lot going on. So we can take it one step at a time. What's the plus 13 on the outside do? Up 13. Good job. What's the plus 4 on the inside do? Left 4. The 1/2 on the outside do? A vertical compression. Okay. Last one of these, and then we'll do the next to the last thing here. So we've got a few pages to go here. What's this one doing? Down 8. That's a good start. The 2/3 do. It's on the inside of the absolute values there, so that means it's what? Horizontal or vertical? Well, it's got to be horizontal because it's on the inside. Is it a stretch or compression? Stretch, because it's a small number. Good job. And then the negative on the outside. That's a reflection across the x-axis. Negative on the outside is going to be across the x-axis. That negative we're inside with the 2/3 would be across the y-axis. Okay. So being able to look at a problem and recognize the transformations that happened. Okay. All right. Let's talk about symmetry next. What is symmetry in a mathematical sense? What do you mean both the same? All right, yeah. So if you cut something in half, if it's symmetric, it'll be the same on each side. So like technically your hands are symmetric, right? You put them together like this and fold it right there. that where that fold together is a line of symmetry, right? So that line of symmetry is where you could cut it in half and it'd match up. Okay, so there's different symmetry that we want to test for with functions. Symmetry could be with respect to the x-axis, the y-axis, or the origin. Okay, and there's a test for each of those things. All right, so x-axis, y-axis, and origin are the different kinds of symmetry that we're going to test for. Okay, so to test for y-axis symmetry, spell symmetry right with an E or Y. Plug in negative x and simplify. If everything goes back to the same, then it is symmetric. Example of that. Let's say we had y equals x squared plus 4. If I plug in negative x, when I square negative x, that means negative x times negative x, right? That's what squaring something means. What's negative x times negative x? Positive x squared. Plus 4 doesn't change because there was nothing to multiply there. So is that back to the original? Yeah, that matches that. So this is symmetric. So y equals x squared plus 4 is symmetric with respect to, kind of a long answer here, the y-axis. Okay. So there's our test for symmetry with the y-axis. All right, so let's talk about symmetry with the x-axis. Okay, so x-axis symmetry. Replace y with negative y and solve for y again. That sounds hard to understand there, doesn't it? I don't know if I worded that the right way. And solve it for y again. If everything goes back to the original, guess what it is? Symmetric. Everything goes back to the original, or the same as the first. It is symmetric. So same problem. Let's take y equals x squared plus 4. If I take that and plug in a negative y, and then I try to solve that for y again, that's really negative 1 in front of the y, right? I would divide everybody by negative 1. That's the rule. To get y back by itself. That's negative x squared. That's negative 4. Is that the same as the original? No, it's completely the opposite from the original. So is this symmetric with respect to the x-axis? No. So not symmetric. once you've done those tests, the origin symmetry both y and x axis. If you're y-axis symmetry and you have x-axis symmetry, you have origin symmetry. You got to have both, okay, to get the origin. All right. So that test, know the test for those, okay? And if you've got the graph, think about folding it. You know, if you've got a picture, you can visualize folding that picture across the y-axis. Does it match up? Across the x-axis, does it match up? If it's symmetry with the origin, you're going to be able to fold it across and then down, and it'll match up then. It would match up in both directions, okay? So it's a little tough to visualize sometimes. But those tests for axis symmetry are, just straightforward. Do those and work them out. It's not crazy. Now, the good thing is that one of those tests is actually another test built into it. And that test is the odd and even function test. The odd and even function test is the same as the y-axis symmetry. What's the y-axis symmetry test? What do? Plug in what? Negative x. Okay? It's the same test for odd and even. The difference is what you get back. Okay? If it's symmetric with the y-axis, then you got to get the original back. So if f of negative x is equal to the original f of x, then f of x is even. If f of negative x, you plug that in, you get the opposite back. Then f of x is odd. With the opposite back, it's odd. If neither occurs, the function is neither. Some of you may say neither. I'm not sure which one's right. The function is neither odd nor even. There are lots of even functions in the world. There are lots of odd functions in the world. There are lots and lots of neither functions in the world. Okay, so be odd, even, or neither, whichever one you want to call it. Spelt the same. Okay, so we're going to do that test a little bit here. Get a little practice with that test and doing a little algebra here, and then we're getting close to getting done here, guys. So almost out of here. I guessed it about 9 o'clock, so it's almost time. So here, let's take a function. I don't know what letter we're on. You might know what letter we're on. F. F. Here's the function. F of x is equal to 8x to the 4th minus 3x squared. And we want to decide, is that odd, even, or neither? So is this odd, even, or neither? I feel fancy when I say it. Maybe you start talking. You ever thought about when you first meet people talking in an accent just to see how long you could keep it going? I just wonder about that. All right. So what's the test for odd, even, or neither? What do we do? Plug in negative x into the problem. So we're taking negative x and putting it in there. And we're working that out. So when you take negative x to the fourth power, what does that even mean? It means negative x times negative x times negative x times negative x, right? What does that equal? A positive number. Why is it positive?
Because negative times negative.
All right, so a negative times a negative, these two become positive. And then if I multiply those two together, they become positive. And then when I multiply those two together, it's positive times positive now. So it's a positive answer. So that gets us back 8x to the fourth. What happens on that negative x squared? Same thing. It's negative x times negative x is positive x squared. So negative 3 times positive x squared looks like that. Is that the same as the original? Yes, that's the same. So this is even because this matches that. That's just where we're plugging it in. That doesn't matter. Good question, but it doesn't matter there. Now, there's got to be a shortcut to this. What do we notice about the original problem? Think about the idea of odd and even. Both of the exponents are even numbers. Think that has something to do with it? It's always going to turn it to a positive, right? It's always going to give you back what you started with. That's always what's going to happen. So the shortcut to that test is if you've got every term has an even exponent on it, then it's always going to come back the same. So if we see a problem, we see all even exponents on the variables, and every term has a variable with an even exponent, then that we know that that's an even function. Okay, so there is a shortcut to it that you can look for. It works every time. Let's take this function. F of x is equal to 6x to the third minus 9x. We want to decide odd, even, or neither. So we're going to plug in negative x. Same rule. Same test. Same everything. 6 times negative x to the third power. 9 times negative x. Well, when I take negative x to the third power, what do I get back? A negative x cubed. So that's going to be negative 6x cubed. What's negative 9 times negative x? Positive 9x. What is that in relationship to the original? It's the opposite. Everybody changed signs. If everybody changes signs, that means you're the opposite, and that means you're odd. What exponent is on that x right there? A 1. What do we know about the exponents 1 and 3? They're odd numbers, right? If every term has a variable and every one of those variables has an odd exponent, guess what the function is? Odd. Okay. The test always works like that, but the shortcut is really nice for that. Let's do one more. F of x, 3x squared plus 5x minus 2. Testing for odd or even or neither. Plug in the negative x. 3 parentheses negative x squared is 5 times negative x minus 2. Well, that's going to turn the x squared, negative x times negative x will be positive x squared. So that's 3x squared. That's the same as the original. So this one's even, right? Wait, I'm not done. I got to do the rest of it. What's 5 times negative x? Negative 5. Oh, that's not the same as the original. Huh. And then does anything change about the minus 2? No. So is that one odd? No, it's not the opposite, is it? The negative 2 didn't even change. The 5x changed, but then the 3x squared went back to the original. So this one is not odd. It's definitely not even. So it would be a neither. Spell neither. Okay. Notice that your exponents, you got a mix of even and odd exponents. Okay. Even and odd exponents mixed together is always going to be neither. Always. So the shortcut is all even exponents, it's even. All odd exponents, it's odd. Got a mix of those, it's neither. That's the shortcut to odd, even, or neither. And you also get the y-axis symmetry with that as well. You know, y-axis symmetry has got to be even functions. They're the only ones that have y-axis symmetry. All right, problems that you could practice from section 2-3, 1 through 85, just the odd ones. Pick some, and you don't have to do them all. 2.6, 1 through 6 or 15. Again, you don't have to do them all. It's not many out of that section. 2.7, 1 through 93. Some odd ones out of that. That will get you some good practice to get you ready for your Canvas quizzes for this week. Canvas quizzes, you'll have one for each of those sections. And then next week, we will have our first exam. We will do labs over these three topics. So I think that there are, I can't remember how many labs next week. 3 labs next week, and then the exam. After the exam, you're done for the week. I mean, you don't have any homework or anything like that. You turn in your test and you go. Make sure you bring a calculator and a pencil. Some of us like pens. I'm a pen person, but you need a pencil to take the test because it's a Scantron sheet. Okay. Before you leave, write your name on the list there. I got your labs, but I want to get that. I'm trying to put some faces and names. I don't see you but once a week, so it's hard to get to know you guys, and I want to. So email me if you got questions.